The demand for electric vehicles and advanced driver assist features has increased the need for intelligent software in vehicles. Cars can now connect to the internet and receive software updates that enhance their functionality or correct errors. Software updates for these cars can also be performed by the user at their own convenience instead of visiting the dealership. In this video, we will demonstrate how Simma Software and Microchip technology enable car manufacturers to implement a secure firmware update solution for modern cars. So why implement a bootloader? During the development of a product, a dedicated debugger interface is used to program microcontrollers. This interface requires an extra access point and is not practical to use after the product is out in the field. A bootloader is a piece of firmware that is used to update the application software after the MCU is released in the field. The application software can be delivered via communication protocols such as USB, SPI, or Ethernet, or in an automotive application, it can be delivered via a CAN FD network. But why implement a secure bootloader? A bootloader alone is not enough. Strong security is essential to prevent firmware from unauthorized or malicious attacks. The security component should ensure that the firmware is not tampered with during its delivery from the manufacturer. It should also provide authentication to ensure that only the manufacturer or an authorized user can update the firmware. Each electronic control unit, or ECU, normally consists of at least one microcontroller where the firmware resides. A normal bootloader in each MCU verifies the firmware integrity using checksums or CRCs. But a CRC can be easily bit-flipped and hacked, so it provides almost no security. With Secure Boot, the ECUs use cryptographic methods such as SHA-256 for hashing to verify the integrity and authenticity of the origin of the software. Security is further enhanced by pairing with secure storage of keys and certificates. The example on the right shows an MCU using the TA100 Crypto Automotive Security IC, which we call a secure element or an external hardware security module to implement security for the bootloader. Not all MCUs have crypto peripherals or the performance to quickly decipher secret keys. Therefore, the TA100 is used as an external HSM to verify signatures to ensure firmware has not been corrupted or changed, securely store the cryptographic keys instead of using MCU flash, and authenticate firmwares by using the certificate chains. In addition to secure boot firmware checks, the TA100 also enables message authentication and encryption. Microchip supports in-house provisioning of secure keys to the device. Using the TA100 has another major advantage. It is compatible with any MCU that uses either a SPI or I2C interface. The TA100 is a security companion that can be added to an existing node that doesn't have security. It's as simple as just plugging it in. If your design already uses an MCU with security features, the TA100 lets you switch to a simpler and less expensive MCU. The TA100 security features can be reused for every node so that you don't have to redevelop the security software. They also reduce the need to provide different provisioning schemes for different MCUs and manufacturers, thus speeding up your development time and minimizing cost. The PIC18Q84 family of cost-effective 8-bit MCUs offers a built-in CAN FD engine. CAN FD provides faster communication than classic CAN. The PIC18Q84 family also supports ISO 26262 automotive functional safety applications. A functional safety compiler is available to help qualify your projects. We selected the PIC18Q84 for this demo to show you how a small microcontroller can be paired with the TA100 to provide enhanced security features. Simma Software is proud to be a Microchip partner. Over the last 15 years, Simma has developed embedded software to support microcontrollers and microprocessors across Microchip's product lines. We specialize in embedded communication protocols such as CAN and Ethernet, and higher-level protocols such as CAN Open, J1939, and UDS. We've sold software to over 1,000 customers across the globe, and our software has been deployed in millions of units. We take pride in our flash bootloaders. We've sold over 100 flash bootloaders with both standardized and customer-specific protocols. We're able to meet any requirements, including encryption and software development guidelines like MISRA. We're proud to be supporting Secure Boot with Microchip's TA100. The Simma Software bootloader being demonstrated today utilizes four components. First, a reduced version of our UDS stack. Second, a CAN driver that is customized for the PIC18 Q84. Third, a security stack built from Microchip's crypto auth-lib with added features to implement secure boot. And finally, either a SPI or I2C driver depending on your hardware to connect to the TA100. In this demonstration, we're utilizing SPI. One feature of our bootloaders is that you can use a LIN version of our UDS stack to utilize only the services needed for the standardized bootloader. This gives you the ability to conserve flash memory. Alternatively, you can add back services to satisfy additional diagnostic needs. Using UDS also provides the advantage of easily supporting other physical layers. The same UDS stack with a different transport layer can support IP Ethernet, FlexRay, K-line, or CXPI/LIN. In this demo, we're going to show three major features of a bootloader with the TA100. First, a successful download and verification of a target application. The image will be transferred via UDS services, its SHA hash will be computed, and then its signature verified against the keys stored in the TA100. Second, we'll transfer an image with an invalid signature. The signature could be invalid because the data in the application file has changed, or because the signature was computed with the wrong keys. In either case, an image will be transferred but will fail during the verification step. Finally, we'll demonstrate how Secure Boot detects a change in flash during deployment and prevents the modified software from running. Because the signature is revalidated on every boot, any change in the data will result in an invalid signature. For this project, we're using the PIC18 F57 Q84 Curiosity Nano board mounted on the Curiosity Nano base for clickboards. We're utilizing two clickboards, one with a CAN transceiver and one with the TA100 connected over SPI. CAN is further connected to two other nodes, our CAN to PC interface for the bootloader host, and a CAN sniffing tool so that we can watch the flow of messages. Here is a demo video prepared by Simma Software utilizing the TA100 to implement Secure Boot. This is a quick demo of Secure Boot in Reflash utilizing the Microchip TA100 and Simma Software's UDS stack. I'm Jake Whiteley, a senior developer at Simma Software. The PIC18F development board is connected to the TA100 over SPI and has been loaded with a signed flash update bootloader. This bootloader is verified by a pre-boot routine before being executed. If bootloader verification fails, the part is held and reset. We'll be able to monitor the bootloader verification steps through CAN messages. We can see here a message saying that the bootloader verification passed, and we can see the 100 millisecond heartbeat being sent by the bootloader. We'll now use our Flash UDS tool to transfer two different application images to the bootloader. The first image is a proper signed application. The second is the same application with some corruption in the middle of the image. This renders the predefined signature invalid. The Flash UDS tool is our implementation of the standardized ISO 14229-1 bootloader host application. It uses our VNA2 USB adapter to communicate with the target. Versions are also available targeting socket CAN and RP1210 adapters. We also offer modified versions meeting various OEM standards. We'll pause the transfer at a few points so we can discuss what's happening. At this point, we've changed sessions, authorized with seed and key exchange, and checked the preconditions. We're now ready to transfer the image. I'll start this process now. This is a valid image, and we'll see the image transfer successfully using the request download and transfer data services. At this point, Flash UDS asks the bootloader to verify the new image. The bootloader transfers the image to the TA100 to generate the SHA-256 hash, and then transfers the application signature at the end of the application file to the TA100. The TA100 verifies the cryptographic integrity of the application through these two pieces. In this case, the verification is successful. The development board will reset, re-verify the bootloader, verify the application, and then start the application. We can follow the CAN messages again to see the bootloader verification, the 100 millisecond heartbeat, and finally the application verification, and then the application heartbeat. This shows us that the application is cryptographically secure and is running without issue on our hardware. These two verification steps of the bootloader and the application take place after every reset to ensure our software has not been compromised. I've now reset the development board to the starting state of only the bootloader being present. The same steps will be repeated, except this time using the modified image which has been purposefully corrupted. The transfer will complete successfully and is again waiting for us at the verification step. When the verification step runs, the SHA-256 hash will no longer be properly verified by its signature, and Flash UDS will report the failure. We also see that after the reset, only the bootloader has been validated, and we're waiting for a new transfer. As previously mentioned, the TA100 also allows us to protect against modifications of the application after it has been written into Flash. In this demonstration, I've programmed a valid image into Flash, which we can see running here. I'll now erase one sector of the application corrupting the part. This is a blunt and aggressive method for corrupting the part, but the verification hash checks every single byte, and so the size of the modification doesn't matter. Now that the sector has been erased and the part has reset, we can see that verification has failed and the part is waiting in the bootloader for a new image. These demonstrations show how the TA100 and the software from Simma can easily add protection to your hardware. Many of the behaviors shown here can be customized to your desired functionality. For example, instead of stopping in the bootloader, the part could be permanently bricked to prevent possible reverse engineering. This demo, utilizing the PIC18F family, shows even the smallest parts can be used in a secured automotive environment. We hope this video has provided you with a basic understanding of how security and bootloaders work together. Please visit the links below for more details. We look forward to helping you with your automotive project.